queue up our first presentation. I'm Bill Oots. I'm one of the sparrows called over from the College for Seniors to moderate the session. So basically what I'll be doing is just timekeeping and moderating the Q&As, trying to keep the program on schedule. There will be time for questions after each set of presentations. The first presentation is going to be epitaxial growth of graphene by thermal decomposition of 6H silicon carbide through carbon dioxide laser ablation. And the speakers are Wren Gregory and Ashlyn, Rickard, and since they'll be presenting jointly, they'll have 30 minutes. So,
thank you.
You may begin your presentation.
Okay. Sure. Hey everybody, thank you so much for being here. I'm Wren Gregory.
And I'm Ashlyn, Rickard.
And we're here to talk to you today about the epitaxial growth of graphene by thermal decomposition of 6H silicon carbide using carbon dioxide laser ablation.
For those of you who are unfamiliar, graphene is a two-dimensional allotrope of carbon that is characterized by it being only one atom thick. It is bound by sp2 bonds, which gives it quite a lot of strength. It is also, due to these bonds, that it forms a hexagonal honeycomb lattice shape. This gives it a lot of properties, such as high electrical conductivity, but this property is also due to its fourth electron free in the third dimension. Now this is pretty important because as far as other nanomaterials go, this is unique in graphene. Now why does this make it significant? It is the strongest material known. Columbia University found that it has the breaking strength 200 times that of steel. Now I don't think anybody is surprised that carbon can be so strong. We're all familiar with diamond. But graphene, being only one atom layer thick, it's just quite significant that it's this strong despite being such a small nanomaterial. Furthermore, it is flexible yet durable. It can stretch up to 20% of its length without losing any of its durability. Furthermore, it also maintains the electrical characteristics. Again, this is unique to graphene and makes it quite useful for industrial uses. It is also 97.7 transparent at optical wavelengths. For comparison, this is more transparent than window glass at 92%. So this already suggests quite a lot of applications of a material that is strong, flexible, and transparent at optical wavelengths. Furthermore, due to the bond structure with that fourth electron free, it is an electrical superconductor. So that allows for zero electrical resistance across the surface of graphene. This also gives it quite impressive thermal conductivity, which we will go into more in a moment.
So now that you've heard a little bit about the properties of graphene, we'd like to tell you some of the current and potential uses in the industrial marketplace. The first, maybe most common use that you might have heard of before is supercapacitors. A supercapacitor is a lot like an electrochemical battery, but some of the problems with batteries on a large scale is that they take up a lot of room and they take a lot of time to recharge. So one of the benefits of capacitors, and mainly supercapacitors, is that you can charge and discharge energy almost instantaneously. Here's an example of a diagram of a supercapacitor using graphene. You can see you have two oppositely charged plates with the graphene monolayers in the middle submerged in an electrolyte solution, and then you would apply a voltage to either side. And graphene is important for supercapacitors because it has a monolayer. It's so thin that you can make a huge amount of energy storage in a very small area. So this gives a lot of potential as far as power backup supplies for industries or electrical cars, where you can charge something up really quickly, you can store a lot of energy, and you can use it really productively just in all sorts of applications. Another really interesting thing that we're really excited about are flexible electronics. This second picture here is a picture of the new Samsung phone, which is supposed to debut in 2015. This phone is largely made of graphene, and they tout that you can bend it in half without harming any of its electrical capabilities. So you can imagine all the wild uses for that, maybe a laptop that can bend in half when you have flexible transistors, touchscreens, and batteries. And then you also have that quick transmission speed that has even been found to rival that of fiber optics in graphene, and that's due to its superconductivity as well. So you might see something like graphene circuits for internet use or something in the future. It has a lot of really interesting capabilities. Another interesting thing are solar cells made of graphene. As I'm sure some of you know, that the current medium for solar panels is called indium tin oxide, and it is only about 12% efficient in gathering power, solar power. And so this has kind of been a wall for a lot of researchers who want to improve this technology and see it more widespread in our communities. And graphene has been found to be 60% efficient at this. So that might provide a huge leap for solar power here in the future. And graphene is also very strong, so it doesn't require a protective coating over the solar panel, which is another interesting attribute. Some more current and potential uses are bioengineering. This is a huge, big field right now for graphene. This is where a lot of the research is in some of our even neighboring institutions like NC State and Clemson University. You can make with graphene what are called bioelectric sensory devices. And graphene is really good for this because it's an organic material and it doesn't tend to interact harmfully with biological matter, which is something that other nanomaterials have been observed to kind of interact a little strange with biomatter, and they may not be ideal for, say, implanting in your body. It might not be safe. Graphene so far has very limited harmful effects that have been observed. So here's an example of a bioelectric sensor implanted on a tooth. So this is a tiny graphene circuit that is able to detect bacterial buildup, what kind of bacteria, how much of it's building up on the tooth, and relay that information back. Here's another example called the artificial nose, which is a monolayer of graphene with a DNA strands stitched on top of it, and this device can detect chemical changes around it, what kind of chemicals they are, how much of them are present, a lot like a nose can. And this was something that we found really interesting, especially for all you science geeks out there, which is a contact lens with a tiny graphene circuit that broadens your visual spectrum into the infrared. So these are some really exciting potential uses of graphene that you might see here in the future, and by getting more productive at making it, it might be more of a reality even within our lifetimes. Some other research going on is in ultrafiltration of water, mainly drinking water, how to desalinate water. These are all things that graphene is being considered for, as well as composite materials like aerospace engineering, using graphene lattices instead of big steel rods will make it lighter, but it's also really strong. Or there's even been research done by coating a whole airplane in graphene to make it really strong on the outside as well as protect it from lightning strikes. So these are all just really interesting attributes of graphene that make it really good for industrial use and really interesting, especially for us here at the undergraduate level, to see where this can take us in the future.
So now that we have discussed what you can do with graphene, how do you make it? There has been success using chemical vapor deposition to make graphene. However, there's another method using laser ablation that we are currently investigating. It has some benefits that are based mostly on the temperature. So we found in our research that graphene can be more uniformly grown if it is heated more quickly and to higher temperatures, which is what a laser is capable of. We are growing graphene on a silicon carbide substrate. We are using 6 layers of silicon and carbide stacked on top of each other. And then when we shoot it with the laser, the silicon desorbs off, and that will leave behind a buffer layer, which is a preliminary layer of carbon that is bonded to the silicon. And then on top of that will form the graphene. Now, going more in depth on the temperature, we want to have a faster surface reconstruction that will lead to rapid nucleation of the buffer layer. So if the buffer layer is not uniform, then the graphene that forms on top of it will also not be uniform. So if the silicon desorbs off more uniformly and at a constant rate, then the buffer layer will form uniformly on top of that. This will minimize gaps and pit formation. So you might notice in this picture here that we have a silicon carbide substrate, and you'll notice the steps and appearances. Those are simply inherent to the structure of silicon carbide. And you'll notice where the arrows are, some areas where pits formed and then nucleation occurred. So when the silicon desorbed off at a non-constant rate, the buffer layer formed in the pit, and then graphene kept forming on top of it to make graphite, which is not what you want. It's useless as far as the industrial scale goes. But you'll notice in the bottom image we have an ideal substrate with graphene on top of it. In fact, you can't even necessarily color graphene there. You can just see the clear steps and terraces of the silicon carbide. So ideally, with the temperature range of the laser and the heating rate, we can create this ideal graphene. However, we do want to note that there is a bound for the temperature, and that is due to the multi-layers of graphene forming on top of each other once you reach a certain high temperature. We hope to determine what this temperature is. Also in our research, we found that an argon atmosphere is necessary to create good graphene. We had previously thought that an ultra-high vacuum system would be what we needed. However, you'll notice in this picture here on the bottom that an ultra-high vacuum leads to the pits, which are the dark areas, and other areas of nucleation, which of course forms graphene that is not useful. However, in an argon environment, in the bottom images, you'll note that you do have steps and terraces with the uniform graphene formed on top. So our next question was, why argon? With our laser system, we already had access to helium, which can also act as an inert shielding gas. But argon, on the other hand, is a little bit more expensive and difficult to get a hold of on an undergraduate level. But we determined that argon also has the property of its atomic radius, which is larger than silicon. So it provides a back pressure for the silicon as it desorbs off the wafer. So this will allow for the silicon to desorb at a more constant rate, which will allow for a smoother buffer layer and then the smoother graphene layer to form on top.
So now that you've heard a little bit about graphene and how it's made using a laser, we're going to further divulge into our experimental parameters. What can we contribute as UNC Asheville students to this whole vast pool of research with graphene, more specifically graphene made with a laser? When we were doing our preliminary research, there was a lot of stuff we didn't understand about graphene. It's a very complicated subject, and we found ourselves asking a lot of questions, like, is there some kind of ideal ablation temperature range? What temperature does silicon begin to desorb off the substrate? And does graphene stop being formed at some point, or do multi-layers simply continue to form as it's ablated? How long does it take to form one monolayer of graphene? And this led us to our ultimate goal with this research here at UNCA. We want to find the correlation between the ablation time and temperature and the number of graphene layers formed on the substrate. In order to give this our best shot, we had to do a lot of preliminary research projects. We've been working on this now for over a year. And the first step that we had to take was the laser itself, getting it to a point where we could actually have a good shot at making graphene. So we had to build and actually rebuild the laser 2 times in order to get enough power for this to be possible. I'm not sure if you recall, but from our previous presentations from last year, we were maxing out at a power of about 3 watts, which we quickly determined was not going to be sufficient for these high temperatures that we know we needed to reach. So, with the help of the undergraduate research program at UNCA, we were able to rebuild the laser with a corrugated tube, you can see here, as compared to the waveguide, and now we're at a maximum power of 20 watts, which is a huge improvement for us. And the shape of this tube actually allowed us to explore with the TEM00 Gaussian beam mode, which is this mode on the left, which is the most universal and fundamental beam mode for a CO2 laser. And that's going to be important for us because we want uniform graphene. We want it to be continuous and all in one sheet. We don't necessarily want to have some graphene over here and none over here. We want to be able to predict where it's going to be and have it be uniform. So we had to take a lot of data with the laser to figure out which was our highest power output line. Carbon dioxide lasers have a wide spectrum of output lines around some central wavelength that you have access to. So for our particular laser here at UNCA, we decided to take power measurements out of all of our available output lines and isolate the most powerful lines that would be most productive for this research. So we found that R24, R22, and R16 all correlated to very high power from the laser system. And our next step was to analyze the substrate itself, the 6H silicon carbide. We know that we needed to get the 6H silicon carbide hot enough for this buffer layer and formation of graphene to occur. So we not only needed a high power line, but we also needed a line that had maximum power absorption by the substrate itself. And there wasn't very much information out there for us on this subject, so we actually had to do this experiment ourselves, which we did last year and actually just published our results this semester. We found that the ideal output line for silicon carbide ablation is R16, which peaks out at 20 watts, and it gives us an absorption by the wafer of 76%.
So this leads us straight into our experimental setup for actually creating the graphene. We have our copper mirror that reflects the beam into a removable focusing lens, and then right into the chamber that holds the silicon carbide wafer. Now, one of the most significant pieces of equipment for us, which was provided by the undergraduate research program, is our optical pyrometer. Now, this allows us to measure temperatures of the wafer and allows us to start trying to find these bounds of when graphene starts to form at what temperature. It also has a fast response time, so we can also note how quickly the wafer is heating up. So this was quite important to us. I'd also like to note that while some of our sources had the wafer in an argon flow, we chose to keep ours in an argon environment at about 1 atmosphere. And we did this by allowing argon to flow through the chamber at about 200 cc's per minute until all of the oxygen was evacuated. So we had 4 samples that we have characterized. The first 2 samples, we used the focus beam. They had temperatures of 950 degrees Celsius for the first sample and 1100 degrees Celsius for the second sample, with ablation times of 1.5 minutes and 2 minutes respectively. We also made 2 samples with the unfocused beam at a constant temperature of 830 degrees Celsius with the same ablation times. Now you might want to note that for the unfocused beam, our temperature was constant at 830 degrees Celsius. So here we could really look at what the time did with a certain temperature. On the other hand, once the beam was focused, we reached different temperatures for different times. So this allows us to really have 2 ways of controlling the temperature. One, focusing the beam or unfocusing it, and the other being the time for the focused beam. Ideally here, we could ablate a sample for 5 minutes and find that we've measured temperatures now upwards of 1600 degrees Celsius, which is currently what we're looking at. After we created our samples, we were able to look at them under the scanning electron microscope here at UNCA, and while we were unable to actually characterize if we found graphene or not, we were able to compare the before and after images of the silicon carbide wafer with not only themselves, our samples, but with published material. So this is the published material here on the left. That is, it has been confirmed that it is graphene on those samples. And on the right, you'll see our second sample. If you recall, this was at 1100 degrees Celsius for 2 minutes. Now, we can't confirm this graphene, but you can tell that there has been some sort of chemical change on the wafer. The lighter portion on top is an area that was not ablated with the laser, and the darker area is where it is ablated. And now if you zoom in, we magnify it here to about 5 microns, you can see this striping pattern that's really reminiscent of the patterns in the published material. So this really got us excited that we had actually done something to our wafer. We just had no idea what.
So that brings us to our next step in the experimental process, which is to actually characterize the samples using Raman spectroscopy. Raman spectroscopy is necessary to determine whether or not graphene is present at all, and you can also determine how many layers have formed on the substrate. In our case, we were lucky enough to collaborate with Clemson University in their nanomaterials research laboratory, where they have a number of graphene specialists, and they were able to perform our first 4 samples in the test on them. So here you can see the Raman spectrum for sample number 2, which you just saw the SEM photo of before. And you can see that it has these peaks in the spectrum that are characteristic of silicon carbide. So this is an indicator that there is no graphene present on sample 2. But to contrast that, we have this Raman spectrum. This is from the Portland State University Nanoelectronics website, which would be what a spectrum would look like if graphene were present. You can see it has characteristic peaks at the wave numbers that are unique to graphene. And then you can also see that by the height of the peak, you can tell how many layers have formed on the substrate. So we're hoping to better understand this in the future and use this in our analyzation of our results as we continue to move forward and make more samples.
So, as we've mentioned, currently we have not confirmed the presence of graphene. However, I think that our SEM images have shown that we have done something to the wafers. we hypothesized that we've actually created the buffer layer, which you might recall is the preliminary layer of carbon that bonds to the silicon. The reason we think this is because we still have the silicon carbide spectra, and we could consider the buffer layer as simply a carbon face of the silicon carbide. So we hope to investigate this further as we move into the next semester. We also hope to look more at the extremes. We want to use higher and lower temperatures, as well as longer and shorter ablation time periods, to really start narrowing down if we formed a buffer layer, if we are forming graphene at all, or the lower bound of when graphene is not formed, neither is a buffer layer. Furthermore, we want to refine the laser's beam mode. As Wren mentioned, we really want access to that TM00 mode. With the laser, every time we turn it on, we have to optimize it. And so we really hope that as we continue this process, we can keep making the beam smaller and rounder and more perfectly Gaussian. Furthermore, we want to investigate the current Raman spectra of the samples and do a little bit more research there as we move into using our UNCA new Raman spectrometer.
So what's in store for spring 2015? The biggest thing that we want to do is to make and test as many samples as we possibly can. Now that we've gotten through the preliminary issues like the laser and everything else, all the backwards understanding, now we can focus on making a bunch of samples and testing them all at once. We also want to bring research students in to continue this project after we're gone. Ashlyn and I graduate next semester, and we think that this is a really cool project that potentially has a lot of use for several research students to come on board. We would like to have people do more of the theoretical side and the Raman side, and just make this a big opportunity for UNCA physics in general. We're really excited about the new Raman spectrometer on campus. I think that this will give us a good chance to get quicker feedback on our samples, whereas when we send them to Clemson, it takes several weeks for us to hear back. This would allow us to get almost, within a couple days, we could know whether or not we had graphene and what direction that we could move in. So this is really going to speed things up for us. We also want to continue to collaborate with Clemson, however, especially if we get graphene, and use them as sort of a quality control. And we want to know, is this graphene useful industrially? Is it good? Is it quality? These are the kind of things that we don't know enough about it to determine. And we're really excited to hopefully get and publish some results by the end of next semester. So we would like to sincerely thank Dr. Charles Bennett of the UNC Astrophysics Department and Dr. James Perkins, also of the UNCA Physics Department, for all of their help in this process, as well as the UNCA Research Program. We'd also like to acknowledge Dr. Rao and Dr. Padala of Clemson University for their generosity in helping us characterize and better understand Raman spectroscopy in general. So with that, we'd like to take any of your questions.
Is it possible that you have got some oxide there
Instead of something else? Yes, sir, I do think that that's possible. We tried very hard to get all of the oxygen out of the wafer chamber, but it is possible that some remaining oxygen was left in the chamber. And this is something that we've talked about, increasing the flow time to better ensure that we don't have any oxygen present. So I think that that's something that we do need to look into. Any other questions?
You indicated you published some previous preliminary results, and you're hoping to publish some more from your work next semester. Where did you publish your previous results, and where are you hoping to publish your results for next semester?
We first published this previous research on the silicon carbide at the infrared wavelengths here at the UNCA Research Journal. So it's going to be published, I believe the research journal comes out very soon, it's December 2014. As far as the other journals, we have several big conferences that come around every few years, and so we're going to submit our findings to some of those. The names are
Big SIRS.
Big SIRS, that was one of the big ones.
Yes.
And we always have the UNCA research, undergraduate research to submit our findings to as well.
And depending on the significance of what we find this coming semester, we'd like to even explore other maybe material science-based or optical-based, more specialty research journals, depending on what we find.
In your research on graphene, what kind of price range, like cost of manufacturing, or did you guys run across any of that in your research?
I did not specifically look into that, but I know that it is not cheap. But I also know that the market's growing, so if economics are true, then I think the cost will go down as you see more of it and becomes more reality based.
I guess another question would be having the experience of doing this research and hoping that maybe some other students will carry on this line of investigation. Where do you see that leading students? What would students who are focusing on this research be looking at in graduate school? Would they be looking at engineering? Would they be looking at physics? Because part of what you're looking at is a production, industrial production sort of process that would be materials engineering. So just kind of wondering what you see as a graduate and career path that this kind of research would lead to.
Well, I know in my own personal experience, one of my top graduate schools is Clemson, and I recently toured their materials laboratory where they specialize in graphene, and this was a big good plug-in for me because I could say I know what graphene is and I have experience in the laboratory setting up research projects. I think that Ashlyn and I, one of the things that we talk about being the most beneficial is that this has been a project where we've had to sort of dabble in all sorts of trades. We got to learn a lot about optics through building and rebuilding the laser and learning a lot of background information that we just had no idea of before. And we got to kind of see the more material science side of graphene and how that's formed and how it's useful. So I think that this would be an excellent research project for anybody because it expands so many different fields. In physics, and which is great as an undergraduate when you don't really know what you want to do yet, this is a great experience because you get to try so many different things all wrapped into one really exciting project.
I mean, I'm on the same page there. I think that the experience you get not only with the optics and material science, but also the instrumentation. I mean, we've had the privilege to learn how to use the scanning electron microscope, and now that we have the Raman spectrometer, I mean, those are useful in every aspect of physics and engineering. Anytime you need to characterize anything on the nanoscale, you use one of those or both or other instruments. Otherwise, just the mere planning and the research, we were lucky here at UNCA to be given quite a bit of free range on where we wanted to take our research, basically. I mean, we always had advisors there to kind of push us in the right direction, but Wren and I did quite a lot of the planning and execution ourselves, which has really allowed us to prepare for any sort of laboratory experience, whether it's in engineering or physics. I mean, I'm going into medical physics, and I know that that will be very useful there, just having the background of how to do research.
Yeah, not to mention the grant writing too. I mean, that's probably important whether you're going to do physics or engineering or whichever little branch you're going to take. You need to know how to get some money to support your research. And
Okay, thank you. Other questions?
Yeah, we still have some time?
Yes, we do. As I say, we're going to try to start the presentations at the scheduled time, and so this presentation actually has another 10 minutes or so allowed. So when the questions are completed, we'll have a short pause. People who need to get a drink of water or something of that sort would have time to do that, and we start the next presentation at 12:40.
Well, in that case, then, could we look at the Raman slide, the slide of the Raman scan again real quick? So, are you expecting, if there was graphene, for the silicon carbide Raman signal to go away?
Honestly, we have only just started investigating what Raman spectra even look like. I mean, there is a lot out there that we've come across in our research, but we've been so focused on rebuilding the laser and trying to get our experimental setup together that we honestly have not looked into this a lot. However, we did meet at the conference we just came back from, Snickers, we did meet with some people at Ablation that apparently had been doing a lot of characterization like this, and they offered to get in touch and kind of show us the way as far as graphene is concerned. So we have no idea. It might disappear completely. It might not.
We could probably find some, you can see like the scale cuts off kind of right where the other one begins, so that's a little unfortunate, but I'm sure that you could find something out there, and we can look into that, get back with you and see.
In the future, you might also look at something very similar, germanium. Instead of carbon, you have germanium.
Oh, I did not know that you could do that.
That's also interesting material.
Okay, well yeah, we'll be happy to look into that.
Yeah.
And I might mention that these two gentlemen you mentioned, Rahul and Polita, they were collaborating with us about 5 years or 6 years ago
Really?
with interesting results we published in Nano Letters.
Was that with the germanium?
No, I'm sorry. No, it's two different things.
Okay, two different. Okay. That's neat though. Yeah, they were really just a blessing for us to be able to talk with, because they're good experts on nanomaterials in general. And then I know that Dr. Rao has won national awards for his graphene research.
So we were also doing nanomaterial with them.
Okay,
That was about 5-6 years ago.
well that's really cool. So the saga of UNCA and Clemson continues. It's good.
Okay, well, any other questions? Okay, very good. That will conclude the presentation.
There's
I've
one
got
more
question that I
Yeah,
want
one
to
more.
put here before we break out. So, thank you so much for the presentation. And my question is, our third presenter is Alan Hawkins, who's working on climate here yet. Alan Hawkins. Okay, very good. Our next presentation will be speed of sound, conduction, and going forward.